So now let's think about pattern classification. So first of all, let's notice that classification is actually generally a supervised learning task, in as much as when we actually build classifiers, we are given input data, but it's also labelled. So in other words, in terms of kinds of machine learning algorithms that this corresponds to, it relates to supervised learning, and because we're doing classification in terms of, if you like, discrete outputs, this differs from another kind of supervised learning where we're actually learning to predict continuous values, which would be regression. We should also notice, though, that you can also do unsupervised learning and discover groups of things and clusters relating to maybe similar kinds of objects. And this clustering can also be used for classification as well at some later stage. But here we're going to think about supervised learning classification. Okay, and that's what we're going to be doing. We can think about what's a typical pattern recognition system for doing classification. And this is really a classical view of what it used to be like before deep learning really took off. And the idea is we'd have some measurement of the real world with some kind of sensor. Quite often we'll these days just get data sets that we want to process, but at some point they have to be recorded, maybe with a camera or something if it's an image. We do some kind of pre-processing on it normally to get the signal in the form that we want to before we digitize it or pass it on to further processing. And then in classical techniques, what we'd do is we'd probably try to extract some kind of features from the data. Although deep learning will do this for us as well, and that's one of the reasons it works better, because we can, if you've got enough data, you can actually get the algorithm to work out what the best features are, rather than some human coming up with the idea that this might be what we need to do. If we can actually do everything automatically, then we generally get better results. And then we have a classification output stage that will take the input coming all the way in, it's been pre-processed, it's got its features detected, it goes into some decision boundary, and ends up being classified into a particular class. Okay, so we're just looking at the top of that strategy there. So there's different ways of building classifiers. Again, machine learning breaks down into supervised, unsupervised. Let's just go down the supervised route. Again, let's just this time just go down the classification route. Various different ways of actually doing this kind of thing. We're only going to look at a couple of things in this course. We're going to look at the naive Bayes, and we'll look at neural networks. But there's other things out there, support vector machines, nearest neighbour, but we're not going to use that either. There are tree methods as well. So, there's lots of different methods to actually do classification and techniques to build algorithms to do this kind of thing. So we're just going to touch on a couple. Because we're going to be doing supervised learning, then our classifiers can operate into two modes, right? And it's going to use labeled data. First of all, there's going to be a training mode when we're actually building this thing up using the training data. And then later when we're actually using it, it'll be used in recognition mode, and it's only got the input, and it doesn't know in advance what the label and what the class is. That's what it's doing for us. It's actually indicating that. So we can think of that in two stages, if you like. We've got the training data set where we've got the data, maybe the images of something in the environment, but we know what the labels are. So we're actually feeding the labels and the data into the algorithm to train the model. And let's not worry about the rest of it, but obviously, how we evaluate it is another issue. But when we've got the model, right, we can then use the model to process data without labels in order to give us the labels. So typically what we do then in a classical, like I said, a classical pattern classifier would be to get the data, pre-process it, maybe get some features, train the model, iteratively maybe till we find a really good way, and then basically end up building this model into a system that can actually do something useful for us. And like I said, if we use deep learning approaches, then it does the feature detection estimation for us as well. So, important thing about pattern classification then is it partitions up the input vector, because we're all going to be thinking in terms of vector input spaces, into discrete regions, right, as opposed to continuous outputs. It's going to be picking things up and putting into discrete regions. Like I said, typically input vectors, we can in general have multiple output classes, and how it actually forms the boundary depends on the kind of classifier you've got. In this particular example, for example, we've got green dots maybe representing one data class, red ones another one, and in this particular case it looks like you might need a sort of circular boundary. In this second example, we've got multiple different kind of classes to be classified. In this case it looks like it's sort of kind of almost a piecewise linear cutting up of this two-dimensional space in order to achieve the classification you need to do. So determining the boundary is really what the classifier training needs to do, and then we use the boundary, if you like, during recognition mode. So we're going to train this then supervised in this particular course. We're going to have a sensory input vectors x1, x2 up to xn, and we're going to give them the discrete labels corresponding to each one of those vectors. So supervised problem, we know the labels, we know the output classes. And the goal of the training then is, we've got this training data set and we want to make sure that we can find the classifier model parameters such that it actually can regenerate the labels in the training data, and then we hope it does the same thing again in the future on novel data and does the right thing. And like I said, there's there's lots of examples of classification. One would be, let's say you've got little images of digits and you want to know which one it is for automatic digit recognition or text recognition. Another good example of stuff which is used a lot these days would be to classify incoming emails as either good emails or spam. Are you being spammed? How can we do that? We need to find some features of that kind of email in various ways. It could also be the content, it could be where it's coming from, and then basically say, is it spam or not spam, and then deal with it automatically. So let's think about a simple one-dimensional classification problem just to get the ball rolling. And what about just a simple speech or non-speech detector using a signal coming from a microphone? Years ago things were done with a couple of operational amplifiers and a threshold. So let's think about some very primitive system that we could use, and it could be that we're just looking for the power in the input signal. Obviously this is a very naive approach. It's not going to distinguish speech from anything else, but it'll tell you if there's a noise. So it's really more of a noise detector kind of algorithm. But imagine we're just speaking into a microphone and we're wanting to build this detector which will tell us when we're actually speaking and when we've stopped speaking, and so whether or not we're actually making a speech sound or we're resting between utterances. That would be a simple example.